The pointing vector does a lot for us, but one of the main things it does is it determines the direction of the propagating wave. And we talk about it usually like this. So if you know a little bit of how cross products work, you can kind of see what's happening here. The way this would work would be the same way as we talked about up here, right? E and B, the cross product of E and B is going to give you a vector which is mutually perpendicular to both. We kind of already did that on the back of the envelope just by saying E if E is in Y and B is in Z, then we're propagating in the X. That's the same thing that would come out of the pointing vector. But there's some other things we can do to talk about the pointing vector. The units here are interesting. So, without going through all the derivations, let me just give you what you get out of this if you put all of the values in and look at all of the units. You get watts per square meter, right? Commonly called intensity. Intensity is a word you could probably imagine how we're going to use it. A really bright flashlight, we would say, is intense. A really dim flashlight, we would say, is not intense. This is going to have something to do with the amplitude of the wave. Right? Amplitude is related to intensity. So think about a sound wave. Amplitude is related to volume. Volume would be the intensity of a sound wave. So right now, the amplitude of my voice would be somewhat low. The intensity of my voice is somewhat low. Right now, the amplitude of my voice would be high, right? The actual waveforms would have a high amplitude, which would be high intensity. For electromagnetic radiation, we can talk about that in terms of brightness, if it's visible light, or intensity is the word that kind of covers everything else, right? If you get a really intense sunburn, that means the UV radiation had a high amplitude for when you were lying out at the beach, right? So we kind of understand that language. Turns out the intensity is going to be measured in watts per square meter. Now watt is the unit of what? Pun unintended. What is this the unit of? Not quite, but close. Not energy. Power. Energy per unit time is how fast the energy is being delivered. So you have certain energy incident upon a surface. Right, here's the surface. So this is energy per unit time and area. Right? So a wattage is intense. And that makes sense in the context of light bulbs, right? If a light is really bright, it's high wattage. We would say that's really intense. What you're saying is the intensity of that power incident upon the area of your eyeballs is painful. Right? That's what intensity is. So the intensity actually turns out to be related to the pointing vector. This actual calculation is definitely not trivial, so we don't ever do it in this class. We instead talk about other ways to do it, which is where this stuff is going to come in. So E and B are not constant constructs here. Right? There's the equation for E and there's the equation for B. These are changing in both space and time. So the way we handle that is by averaging. Right? That's always what we have. That's always the way we handle constantly changing constructs, is by averaging. So the point of all this, and I apologize if it was a little rambling here, switching gears on the fly here. Intensity, usually denoted with an I, is the time average value of the pointing vector, which we will express like one of the following. There it is in terms of the electric field. I think you can probably see the relationship between that and the energy density. Intensity and energy density are proportional. Turns out they're proportional through the speed of light. Right? So that's the time average value of the pointing vector in terms of the electric energy density. But we can do it with the magnetic field as well. Both of these equations work. one gives it to you in terms of the electric field, one gives it in terms of the B field. You can manipulate these to get it in terms of both of them if you so desire. Right? But this is what we would call the intensity of a wave. We're going to see next time a little bit more about how that works. So if I lost any of you today, I'm going to take some responsibility for that because I had to switch gears. I'm also going to throw it backwards on your 16th teachers. But you would have done waves, right? They're all my friends. I've done with them. If you have questions about any of this, if I lost you anywhere, please come chat with me. I'm happy to fill in some gaps. If all this is new to you, please go back to University of Physics Volume 1. Read the chapter over waves and wave propagation.